Okay, we'll go over this. It's a very short presentation. That's number 10, Sarima model building. That we're just going to go over the process for model building. I mean, the overall process we have already discussed. First, we identify if we need to make a transformation to stabilize variance. Then we identify if we need to take differences. And now what's different now is that we need to detect if we need to take non-stationary differences, normal standard differences, let's say, and if we also need to take seasonal differences, seasonal differences. So we're going to work now with a set of data that has set this information from January 2010 through December 2016. And we'll go over the R code now, but anyway, this is the graph, the plot of the series. As you can see, there's a trend. And so this is an indication, a clear indication that we will need to take a difference, at least one difference. Okay, we don't know yet if we need to take also a seasonal difference or not. We don't know yet until we analyze the ACF and PACF of the series. So, but we know we're going to have to work with the first difference. And if we look at the first difference, that's the second chart here. Now we've removed the trend, and there are some doubts here as to whether or not the variance is constant. If you look now, and in this graph here, it's easier to see if the variance changes. Apparently, I have larger variance towards the end of the series than at the beginning. Okay, that seems to be the case. So we need to check if we need to make a transformation. So if we're going to run the Box-Cox function to understand what the optimal lambda is, and turns out that the optimal lambda is 0.5. Okay, now 0.5 is close to 0, and since we know that we're going to have to difference the series at least once, then it makes more sense to work with the logarithm, because that the difference of the logarithms will be the log of the ratio. So that it's a log of the rate of increase or decrease of the setes. So one way to check if I use 0.5 or if I use the log, the natural log, is I can grab the original series, the series to the 0.5, and the series with the logarithm, the logarithm of the series. And as you can see, from 0.5 to the log, there's not a big difference. So at least visually, there's not a big difference. And we can start trying to work with the logarithm of the series because it makes more sense to work with the log than to work with the series raised to the 1/2, to the square root of the data. Okay. We're going to see this is the ACF of the series. Can you help me with there with your mics? So that's the ACF of the original series and the partial autocorrelation function. And this is the ACF of the difference of the series and the partial autocorrelation function. Now, one thing to notice here, look at this plot. That's the original series, then the series raised to the 1/2 power, and the log of the series. Visually, there doesn't seem to be a huge difference between the three. So we either work with the original series or work with the log of the series. Okay. And here we're looking at the ACF of the series and the PACF of the series. So from this PACF, we know we have to take a difference. Okay, we know that we need to difference the series at least once. But if you look at this ACF and the PACF, it looks like it could be an AR1 model, but with the first coefficient very close to 1. So that would mean that you would have an error model for the phi would be very, very close to 1. If that was the case, then it's almost like taking a difference, right? And now we see the series, once we take a difference of the series, and we observe the ACF and the PACF. Now, here, if you can see, for example, it's easier for me to. If you look here at this ACF and PACF, I'm not recognizing my pencil, but anyway, look at this thing. I'm going to use the annotate from here from my screen here. So let's look at this point here. That's month number 6. That was meant to be a circle here. That's month number 6. And this is month number 12. There's nothing here. Month 18. There seems it's getting close to the bands, right? To the confidence bands. And we're seeing also in the PACF that we observe some significant lag in lag 18, which is a multiple of 6. And if you look at lag 6, it's close to the boundary here. It's close to the boundary. So this is an indication that I may have some seasonal behavior with periodicity equal to 6 months. At least it looks like that from this chart. So now let's look at since we're seeing that we need to make a difference, we need to take a difference, okay? And if we look at this ACF and PACF, what we observe is that there's nothing here at the beginning, okay? I don't have any significant lags right at the beginning. The first significant lag occurs at lag number 6, and then at lag 18, for example, that's a year and a half later, and so on. And you observe similar pattern here. We have something significant at 18 and something that seems to be a significant lag at 6. But in this case, in the PACF, it's not clearly significant here, but it is in the ACF. So that may be an indication that I have a moving average model with a seasonality 6, a seasonal moving average model. So that's what the first model we're going to try here. We try to fit an Sarima. I don't see any other regressive terms in the ACF or PACF of the non-seasonal part. There's one difference. We need to take one difference, and then we have zero moving average terms that are non-seasonal, and we have one seasonal moving average term, because we only have one in the ACF. We only observe that the 6th lag is significant. The rest are 0, essentially. The rest are non-significant. So that may be an MA, but seasonal, with E equals to 6. So that's why we fit a Sarima model with a seasonality of 6 months. And we looked at the graphs of the residuals. The normal graph deviates a little bit, but not much, nothing really serious to worry about, because this is happening because we have a few outliers in the series. When you look at the series, we have this point, that these are the residuals, but this point corresponds to an outlier. These points are also extreme, and this one probably also. The ACF of the residuals looks very well. It just shows that there is no autocorrelation, and the P values for the junk box statistic is also looking good. Okay. Now, if we were to choose the logarithm instead of working with the original series, okay, so working with the log of setes, we see that we also get an appropriate model here. It looks very similar. The diagnostics look very similar. So we could work either with CETES or with log of CETES, and in both cases we get a reasonable model. Okay, so if we prefer to work with the original units, we would work with CETES. Okay, there's no need for transformation here. Now there's other criteria that we can use to select the right model. One of the criteria is called the Akaike information criteria. Akaike information criteria is essentially the ratio of -2 times the log of the maximum likelihood function. Okay, so once we maximize the likelihood to obtain the parameter coefficients, that maximized likelihood, we take the log of that maximized likelihood and add to R. R is the sum of P, the order of the P autoregressive terms, the Q autoregressive moving average terms divided by N. That's the Akaike information criteria. And what we want is a number that's as small as possible. Okay. So this is the criteria that is used by some of the algorithms that automatically select a model. Okay. For example, the autoarima function in R automatically fits a model, but the only criteria it considers is the Akaike information criteria. It tries to minimize the Akaike information criteria and selects the model that minimizes that. However, this criteria doesn't take into consideration whether the assumptions of the model are held or not. Okay, it doesn't check assumptions, so the model could be violating some of the assumptions, and that function, the autoarima function, will select the model that has the lowest Akaike information criteria. And there's another criteria that's also used, which is the Bayes information criteria. It's very similar to the Akaike information criteria. If you see here, the Akaike information criteria is approximately equal to the variance, to the log of the variance of the residuals, plus R divided by times 2n, times 2 divided by n, plus some constant. Whereas the Bayes information criteria takes a log of sigma, which is the same thing here we have here, plus R, and now takes the log of n divided by n. R is exactly the same as in the other case. So in both cases, whether the function uses the Akaike information criteria to select the model or the Bayes information criteria, we look for numbers that are small. Okay, that's what we're looking for, numbers that are small. Now, Bayes information criteria imposes a greater penalization to the number of parameters in the model than Akaike information criteria. Now, if we have a seasonal model, then the R is not only the autoregressive number of parameters, but also the seasonal number of parameters. Okay, so we will consider that. Now, let's work with this series, the monthly AT&T returns. Well, let me go first over the script of this series that we just analyzed, the CETES. That's in a script called ST10 Construcción Modelos ARIMA. Okay, ST10 Construcción de Modelos ARIMA. Download that script. You're going to use it to analyze the other series, and we're going to read the CETES data, which is an Excel file, and run up to line 27, so that you have your data in your workspace, in your environment already.
Ready, teacher.
Okay. So as you can see, the CETES data has the date, and then which appears as the first day of each month, and then the value, okay, of CETES. Now, let's make it first a time series. So I converted with the TS function, and I make it, so I take the column named series, and set up the start date, which is the first, in January, it's January 2010. Frequency equal 12 because we have monthly data and we have 12 measurements per year. So that's now I have made it a time series. That's the plot of the series that we already saw in the presentation. And that's the plot of the first difference of the series. If we look at the Box lambda, it gives me 0.45, which is very close to 0.5. So I can try to make the plot that we showed you in the presentation, where I show the original data, then the transformed data with the optimal lambda, and the log of the data, which is close to the optimal lambda, but it's halfway between 1 and 0. I do that thing. I plot I put everything in I column bind the three series, the setes, the set is transformed with 0.5, and the set is transformed with the logarithm. Okay, and this is where we see that there is no big difference between the three plots. So we can work with setes with the original data, and that's the ACF and the PACF of the original data. Okay. And now it's clear that we need to difference because the rate of decay is very low. Okay, it's decaying to 0, but very low, at a very low rate. So that's a clear indication that we need to make a difference, take a difference here. And if you see, if you look at these plots, with these plots, you cannot distinguish the seasonal component because we still need to make a difference of that series, take a difference of the series. So I'll call D1 setes the first difference. And then now look at the ACF and PACF, and we observe what we saw earlier. The ACF has a significant lag in lag number 6. Okay, there's nothing before that. So in this area before lag 6, there's nothing. And there's nothing here in the PACF. So that leads me to believe that this is an MA model, but only seasonal, because I don't have any correlation structure at the beginning of the series, at the beginning of the lag. So the first few lags, I don't have any correlation structure. So it looks like I only have a seasonal series. Okay. Now I have a seasonality of 6. What happens if I take a six different seasonal difference? So that would mean that I would take ZT minus ZT minus 6. So I would take D, and I'm calling that D6 of D1 of the first difference of series, to take as a sixth seasonal difference. If I do that, and I look at the ACF, now I see only noise. Okay, I'm over differencing, and I can calculate the standard deviation of the series. Here's the standard deviation of setes. This is the standard deviation of the first difference, and this is the standard deviation of the sixth seasonal difference of the first difference of the series. And as you can see, the standard deviation increased because I'm over differencing already there. So I don't need a seasonal difference. All I need is the non-seasonal difference, and that's it. Since I'm taking one difference and I'm working now with the original series, I'm going to use the SARIMA function for the series setes, the original data, 0 autoregressive terms, 1 difference, 1 non-seasonal difference, 0 moving average terms, non-seasonal moving average terms, 0 autoregressive seasonal terms, 0 differences, 0 seasonal differences, and 1 moving average seasonal term with seasonality equal to 6. Okay, that's the order P, D, Q in lowercase, and then capital P, capital D, capital Q, and then E, the seasonality. Okay, that's the order always in this. I'm going to write it down here. Is SARIMA, and then it'll be series, then it'll be P, D, Q, P, D, Q, and E. Okay. Now, if I don't specify any of these, that means that there is no seasonal component. So those are the we see that we fit the model Sarima with setters like that. And if you look at the coefficients of the model, we see that the coefficient is significant. How do we know that it's significant? It's statistically significant, different from zero. I don't have a p-value here. Down up here don't have p-value. It's right here, right? It's right here. But if I didn't have that information of the p-value, how do I know if this coefficient is significant or not? If I take the estimate, theta hat, and add and subtract 2 times the standard error, and that includes 0, then it is not significant, statistically significant, different from 0. But if it doesn't include 0, which is this case, if I take, I add and subtract 0.3 from this number, from the estimate, and 0 is not in that interval, so I know that it's significant, and I have the p-value here. P-value is 0.01. Okay, so this p-value is testing the hypothesis. Again, it's always the same. It is the hypothesis. In this case, it's only one parameter, that capital theta equal to 0 versus the alternative that theta is different from 0. Okay, so that's significant value. And if I do if I were to fit the model for if I were to fit an autoregressive term here for the series, look at what happened here. If suppose that I started with this thing, assuming that I had one autoregressive term that's non-seasonal, then it would not be significant. Okay, so if I had started here saying, well, what if I have an autoregressive term and I fit this model? It will turn out that this coefficient is not significant. So I don't need this coefficient. Okay, the right model is this one, and it also works with the log of the setters. It's the same model, and it gives me reasonable diagnostics. Okay. Now, if I can work with the original series, I prefer to work with the original series because when I forecast, I don't have to transform back. If I were to work with the log, when I forecast, I will be forecasting the log, and I have to take the exponential of the forecast. And I would have to adjust the confidence intervals because of their transformation. Okay. In this case of the log, no, because it's a monotone transformation, so it shouldn't be much of a problem there. The intervals will be very close. So now I'm going to split you in groups, and I will let you work on the series. Monthly AT&T returns and monthly car sales in Quebec, at least those two series. Okay, monthly, I stopped sharing, but anyway, let me put